Hello and welcome. This is Team 1, and we are here to present our concept called the Speakeasy, which is the first smart speaker that lets your vibe be in control. So, we're going to talk about a few different areas of it. First, we're going to start with what are the issues today with smart speakers? And the problem, really, the crux of it, is that they are reactive. They wait to be told what to do, but really, how smart is that? One aspect that we want to talk about is conversation. So, you ever tired of screaming over the music trying to talk to someone? We're too. Being human is really about connecting in those spontaneous moments. So isn't it about time your speaker let you do that as well? The vibe. So music and people are dynamic. Things are constantly changing, but the current speaker systems that we have are not. So sometimes we want to relax, listen to chill music, but sometimes we want to dance, and the vibe can change quickly. And our speakers, unfortunately, just don't know the difference. And safety. There's a study that shows that in the US, 24% adults and 17% of teens are affected by noise-induced hearing loss. Your smart speaker should really have your back. Music is meant to create the vibe, not to kill it. So what we propose with the Speakeasy is the first ever proactive speaker. We react as things change so that you don't have to. With conversation, Speakeasy uses powerful AI to determine whether our speech is conversation, whether it's cheering, whether it's just the music playing, or whether we're laughing with friends, so that you can keep being you no matter what. Speakeasy also uses motion and voice sensing technology to adapt and enhance the mood. So when the energy picks up, your music does too. And when conversation strikes, the music won't get in the way. And lastly, safety. Speakeasy monitors the volume level and offers two operating modes. We have a safety mode, which you can set where the volume won't exceed a certain limit. We also have the user mode, which notifies the user if the volume exceeds that limit. The speaker should bring the same energy you do, not the other way around. So now we can talk about the market. So wireless and smart speakers are dominating American homes. Study shows that 1 in 4 Americans have a smart speaker in their home, and that the number of smart speakers has grown 135% in the US in the last 2 years alone. Additionally, there's a projected 163 million units sold globally in the next year. The problem is the smart speaker market is highly saturated with large companies. If you look at some of these big headlines that Amazon and Google, which I'm sure you're familiar with, are actually losing money in the speaker price war. They're just trying to get their devices in your homes. So what we propose is that we position ourselves as a premium smart speaker controller. That way you can upgrade or retrofit an existing speaker for enhanced control and additional features and automations. As far as the demographics we're looking to address, we know that smart speakers are typically shared by a household, and because of this, that means that different age groups and different music uses. So we promise an adaptive control solution that listens to those listening. As far as the needs, we know that social environments are constantly changing, and so are the people. You can go from a very lively, uplifted mood and then to a conversation mode, and it should be able to go seamlessly in between the two without the music getting in the way. And as far as income, Pew Research Center cited that people whose household income exceeds $75,000 are over twice as likely to have a smart speaker than those with an income below the $30,000 threshold. And of that, 60% of people cited price as the main factor for not purchasing a smart speaker. So this uniquely positions us because there's not enough market penetration at the lower price point. With Speakeasy, you can retrofit your existing speaker, which offers a low-cost alternative to purchasing a brand new smart speaker. And then as far as the business model, we believe that turning any speaker into a state-of-the-art smart speaker by connecting the Speakeasy controller is the way for the future. So as far as features, it will enable users to convert any speaker into an internet or Bluetooth capable device. We have powerful cloud-based AI that can dynamically control music in the setting that you're in. We have safety features that ensure your ears are protected, and that we are also working on an app interface that allows users the ability to customize preferences for all of these aspects. And then for the future of Speakeasy, where we'd like to see this product go, is that we could begin to aggregate data and let users know how songs stack up against the crowd, what vibes come about. We'd like to be able to have multiple users controlling the same interface so that there's no need for song requests anymore. We would have an offline mode that allows the core functionality with no internet necessary. We also want the ability to control a smart home or multi-speaker system all on one easy interface. And additionally, we would add features like automated music playing for certain times of the day, customizable acoustics for songs, and more features as they come up. With the Speakeasy, we believe that the future of smart speakers lies in proactive speakers, ones that not only understand the vibe that you're trying to create, but help create it with you. So now I'm going to discuss the technical system overview for our Speakeasy device. So as you can see here in the diagram, we have at the top an AWS cloud. That's where our EC2 instance is being hosted. And you can see on the bottom left, we have Android accelerometer data. So these are our IoT distributed devices, and these would be what people would be holding on to using while they're listening to music in the vicinity of the device. So that data is going to be constantly streamed, the accelerometer data that is going to be constantly streamed up to the cloud. And then on the bottom right, you can see that we have our Speakeasy controller, and it would be configured to a speaker via an aux cord. And then this device will communicate with the AWS cloud, sending audio recordings of the environment, and as well as receiving commands for changing the volume output on the speaker accordingly. So now taking a dive in for the machine learning, it is an audio analyzer. And so we adapted some code from a Google project, and this has two main aspects to it. And we take in an audio file, and it does a feature extraction, and then it does a classification on that data, on the features that are extracted, and then it basically creates confidences on what the category of speech or audio it is. So as far as the feature extracting, it takes this raw audio data and then it creates a dense vector of features. So we played around with the parameters of the recordings that we wanted to use, and we found that the best sweet spot was around a 5-second WAV file recording. And the 10-second was too much latency in terms of putting results out to the Speakeasy device, and a smaller 2-second WAV file was not sufficient in order to really get a better picture of what the environment is like. So these examples, the features are extracted, and then that data is going to be sent over to TensorFlow, where we're running our machine learning algorithm to be able to classify these. So then in the classification, like I said, it's a model adapted from a starter code that was on Google's YouTube 8M project. And so it's a certain logistic model, and it takes these features that were extracted, and then it outputs a map of different audio classes and their confidences. So the model's trained on audio set dataset, and then we deployed the trained model on our EC2 instance so that the inferences can be made in real time. And what we did here is, like I said, there's a long string of features, and we basically chose out the ones that we thought would be most pertinent to our project. And those were included music, musical instruments, laughter, speech, conversation, and cheering, because we really wanted to be able to differentiate between when people are actually trying to have a conversation and whether they're, singing, cheering, screaming along to the music while it's playing. So there's a big distinction there, and that's what we really aimed at trying to tune between. So then we look into the system controller. And so this it has 4 key aspects of operation. And so one of those is hosting a TCP file server and a TCP Android server. So the file server is where our files are streamed in from our Speakeasy, which is a Raspberry Pi running our other code. And so these recordings are made, and then they're constantly sent to this file server, which is just listening and writing files to a directory on the AWS EC2 instance. Same thing for the TCP Android server, except that is a much lighter weight data being sent. It's just a simple vector of 3 XYZ gyroscope coordinates, or values, excuse me. And so those are processed as well. And so we also have a command interface with the Speakeasy. So this is just a direct TCP socket, and we're using it as a half duplex. It's just unidirectional, going from AWS to the RPi, and that's to send commands for increasing the volume, decreasing the volume, as well as there's options to perform other commands for future iterations. And then we also have the classifier interface for audio recordings. And like I said, this is what I was talking about before. We receive the audio recordings, and then we have to send those over to the classifier. And then the last part is just processing that accelerometer data. So as far as the classifier interface, there's the AWS EC2 instance. It streams the audio, and then it inputs that into the feature extractor and the classifier, and we get out that the particular vectors that I talked about before that we actually want to use with. So those confidence intervals that we can weight into our algorithm that we implemented. So that's speech, conversation, laughter, cheering, music, musical instruments. You can see on the flow diagram at the bottom, we put in the audio recordings, classify, and then we get these results that we can actually utilize in our overall algorithm. So then as far as the communication interface, you can see on the right, this is a little bit of a flow diagram for how it works. And I kind of explained it before, but it has 2 servers that it's listening on, and one of which is for Speakeasy. It's just sending the files, and that's noted as number 2. And then there's a noted as number 3. That's the server where the Android accelerometer data is coming in. So we can have, several different devices coming in, as many as there are available essentially. And we currently tested that with 3 devices. And like I said before, the Speakeasy command interface is just a one-directional socket TCP that will send commands over that interface that remains persistent throughout the connection. And then as far as the actual controller code works, it uses that audio classification as well as the accelerometer data, and that we can use to kind of get a picture of what the user environment is. And so it weights, we have a way of weighting these inputs, the audio and accelerometer, and the controller algorithm determines how to correspondingly adjust the speakers based on the environment. And so those commands are then relayed over to the Speakeasy in real time. So we can, hear the volume changing as the conversation. So that's as far as it is from the cloud. And then in terms of the code actually running on the Speakeasy controller, we can look in here. And so basically we're using a Raspberry Pi 4 interface. It was something we had available, and it has plenty of processing power to do the job. And something for the future, it could be probably a lighter weight CPU. But the 2 main aspects of operation for this is the communication with the AWS EC2 instance. I alluded to a lot of that before, and then also just the processing on board and how that's handled. So as far as the communication, it's the same TCP connections, and so we're receiving commands from AWS, and that socket is a single thread, and so all those commands that are coming in, we add them to a global queue, and then these commands can then be processed by the main execution thread on the Raspberry Pi to actually change the audio. And then as far as the files, there's a TCP server always running on a designated port, and so every time we make a recording, we spawn a thread, and it's responsible for establishing that TCP connection to the server on AWS, and then we send the file over to them. And as far as the actual main execution segment on the Raspberry Pi, we have 3 processes or threads that are always running. And so there's the main music playing process, it's just the music playing process. And what that does is it's spawned from the main execution loop at the beginning. And we use this OMX player, which is a really lightweight command line interface for playing media, and it is particularly made for the Raspberry Pi actually. So we're able to just spawn a separate thread that executes a command and runs that script. And so then basically by communicating with that ongoing thread, you can, via the command line, you can actually change the audio output accordingly. So that's one aspect. The recording process is another aspect. And similarly to the music process, there's a command line service that we can use called a record, and a record basically will utilize whatever speaker is configured to the device. So we're using a microphone that connects via USB to the Raspberry Pi, and then once we spawn that, it'll make a recording for a set interval of time. It will save the file to a certain directory, and we chose to use wave types, and we're sampling at 44.1 kilohertz at 16-bit samples. So really high fidelity audio that's coming in. And these are basically however often as we can, close to continuous. So we have to quantize the time. So essentially every 5 seconds we make a new recording and then we send that off. So that way in the classifier can get that information in time to actually help make a decision for how we should change the speaker output. And then the main execution is basically just managing all these threads. So that will receive, like I said, the commands from AWS that are loaded into that global queue, and then it will execute any of those commands by calling a function on the music process, which basically just feeds in a command line argument to that the running process for music. And the same way for we keep a queue of audio recordings, which are the names of the files as they're recorded, and then we use that to send them off to AWS. So anytime that we have audio recordings going or available to send that we haven't sent yet, we send them off. Once they've been sent and we know that they have been, we can actually just delete them right off. So we don't actually keep any files on the Raspberry Pi, or we keep as minimal as possible since memory is, we're using a 16 gigabyte SD drive, so we don't want to waste too much space on that. And then as well, the main execution process manages error handling and connection reestablishment. So even in the event that we lose connection with AWS, it will persistently try to reestablish that connection. And as soon as the server's back up online, we'll begin communication as we had before. So you can see on the right, this is a little bit of a flow diagram explaining the process. There's files going out from the Speakeasy to the TCP interface, and then those are commands coming in. And then each of these arrows is meant to represent invoking a process on the Raspberry Pi. And so this is the entire system for our AWS IoT project for Speakeasy. And then we're going to show you a demo that actually working in real time, reacting to conversation and different in dynamics. So we can give you a demo of that.
So this is us starting the RPi command script over here. So we just have to run this simple command. And you can see that the music has started. You can hear it. And currently the server is not up and running, so it will just persistently try to reconnect. So this is part of the error handling that we have in here. So you can see that now it's connected, and some of these printouts finish sending file, that's saying that it's sending this recording file. So currently we have it at 2-second intervals, and it will be continuously sending those over to the Amazon EC2 instance.
So to launch the process from the cloud side, all we really need to do is to activate a conda environment and simply run the script python3 controller.py. And the process is launched.
Oh man, I really like this song.
Yeah, so I mean it's an oldie but a goodie.
Yeah, it's a great
That
song.
funk goes way back. So wait, you were telling me you just had a final in 550, right?
Yeah, I just had a final in 550.
So how'd that go?
I don't know, it was pretty tough.
Really? Yeah.
Yeah.
What was the topics on?
Eigenvalues.
Really?
Yeah.
So you're doing linear algebra. Are
Yeah,
you taking
yeah,
a class next semester on that? Is that your plan?
Yeah, that's my plan.
Really?
What about you? What class do you take next semester?
I mean, we're gonna take that operating systems class together. I think that's gonna be
Oh,
good.
yeah. That's
And
gonna be a good class.
I'm debating to take one of the FPGA accelerated computing classes.
That sounds like a good class.
Yeah, I feel like that'll give me like a good threshold going into industry.
Yeah, no,
Especially since I'm gonna be working on a lot of that.
Yeah.
Well, I don't really need to like talk about it anymore.
I know. I feel like before the music was so loud we had to raise our voices. And now
Does
the
seem
music
that
is
way.
just like going down to accommodate our conversation.
It's beautiful how it works like that.
Yeah, that's really nice.
Thanks, Speakeasy.
Yeah.
All right, this
Wow, Tristan, that was such a great song.
I know, dude. I couldn't stop moving.
Wow, yeah.